My name's Neil Hand. I'm from Codasip. Codasip is a Czech IP and tools vendor. So I may have to disagree with the Austrian about where the center of Europe actually is. Is it Czech Republic or Austria? That is probably something up for debate. But I'm here actually talking on behalf of a number of different companies, and I'll explain how that all comes together. The core of what we're going to talk about is achieving the same type of thing Jack was talking about, which is, how do you solve this problem of every design is unique. You really want custom silicon. You do want to be able to have a processor that's optimized to your need, the platform that is optimized to your need. And until very recently, you didn't have any other options. Jack presented one option with what SoC are doing. I'm going to present another way where we've got multiple companies working together, because the existing solutions are insufficient. The standard parts are good, but they're just suboptimal. They don't scale very well. ASICs are too expensive. If you want to do it from the ground up, build it, as Jack was talking about, the IP is expensive, the tooling is expensive. So how do you solve this problem? This becomes especially important when you look at IoT companies. The reason that we started working with a number of other companies to do what I'm talking about today is we're getting companies come to us that have never done ASICs before. And say, we want a RISC-V core, but we also want to be able to do everything else around it. And we want to be able to keep control of our own chip. So how do you solve that? Because as a design moves along from getting the basic functionality to market to the second and third generation designs, you need custom solutions. But there's a gap. If you took the traditional approach, you need millions of dollars. And you don't have that sort of budget. So we're looking at how we can make it cost-effective, time-effective to get custom silicon for those phase 2 and phase 3 products. Some of the industry things is helping us as well. So if you look at traditionally, and again, this is just a different way of saying some of the things Jack was talking about, you can now get, for IoT class designs, you can get extremely cheap implementations where you're talking in the tens of Ks to start getting prototypes and production chips. That is vastly different than if you're looking at off-the-shelf components. And the good news is, if you look at a lot of the industry data, for the first time in a couple of decades, people aren't saying design starts are declining, because even though there's consolidation, Semico published the report earlier this year, and there's significant growth in what they're calling the basic SoCs and smart sensors and analog mixed signal. So the growth is there. These customers are there. We talk to them every week. So the question is, how can we help them get a design more easily to market? And that's what we set about doing. So we went out, as we hit different problems, as our customers were asking us for different capabilities, we went to a number of our partners that how can we build a whole platform that keeps the designers in control, lets them build their own devices, but does it in a way that is time effective and cost effective. And we looked at it, how you can do it in a way that starts from the bottom and then builds up to the point where you can do high level programming. So we started off at the bottom level, and I'll go into each of these different areas with one of our partners, Baysand, which is doing, and I'll talk about their solutions, but it solves the problem of getting to implementation, of getting proven IP out there. On top of that, we've got debugging. Debugging is important. I'm probably going to get a question, I guess, from Samsung later on that question. So we've got debugging on top of that. We then have the processing and software infrastructure. And so the idea is build this nice, simple stack so someone can sit down with RISC-V and get it working quickly, easily, without complications. It's all standards-based. Everything we're doing is based on open standards, open APIs. None of the solutions I'm talking about, though, are open source. So I guess I'm the first person up here that doesn't say open sources. I'm not going to open source all of our stuff. What we are is we're all commercial companies, and the idea is we are the throats that customers come and choke if something goes wrong, and that's an important thing for many designs. But we are, it's all centered around RISC-V and the RISC-V standards. We're using LLVM, Eclipse, System C. Across the board, if there is a standard interface we can use, we use that standard interface. This is good for two reasons. It means anything we do, any of the companies that I'm talking about, it's fully utilizable by someone else. So we're not trying to lock anyone in. We're just working with all these open standards. So it starts at the silicon level. The biggest challenge for many customers, and this is what Jack was talking about, is how do you get these designs to market? How do you get them built quickly, cheaply, and with low risk? So we started working with Baysand a while ago. Some of our customers are working with them before. And what they do is they have a solution that allows you to go from the handoff of RTL to them using their IP libraries to working silicon in an order of weeks, 7 to 10 weeks for 65 and 40 nanometer designs. They will also do FPGA porting, but the key thing here is getting that window down from the 68 weeks that may be typical for these process nodes down to 7 to 10. Do it in a way that is in the tens of thousands of dollars. The magic number, I think, is the one that Jack was mentioning, which is sub 100K. If you want to get these things done for that sort of pricing. So the way they do it is they have their metal configurable standard cells. So this idea here, it's with multi-project wafers as well. So what they have, you've got 600K to 4 million gates, you've got lots of IOs on there, lots of memory capabilities. They've got the DCMs and the PLL, so they've solved a lot of these challenges that people were talking about earlier. You've got the packaging is included. And what you can do is you've got an RTL sign-off. It's very low cost for the verification of these designs. You get 100 fully tested parts, and it's 8 weeks from tape out. But they've got all the core IP you need, all the IOs. It's metal configurable, it's quick, it's simple, and you've got it back, and it can be working. They'll also do, for customers that are moving along that migration path, they can use the same technology with some additional tools that they have to do metal porting of FPGA. So you give them the design, and they will move it across. So at that point, we've now said, okay, we've got the implementation taken care of. There's a way to quickly and easily get from your design into implementation. What's the next level on top of that? Well, the next level at the RISC-V conference, you need IP. Now, Codasip is an IP company. We've got a range of different IPs. In a nod to our friends at Berkeley, we called our RISC-V ones Berkelium. We've got 2 of those. We've got a 3-stage and a 5-stage. They're inspired by Zscaler and Rocket, but they're not clones of them. There's lots of different capabilities in these cores. They support all the standard extensions. If you look at the data, and the slides will go up, they're roughly on par with the open source solutions that are out there. They're slightly better in terms of frequency and power. But these are production-proven RISC-V cores. But more importantly, they're easily modifiable and extensible. I think so far every talk has talked about the advantages you can get from customizing the instruction set. The reason Codasip got involved with RISC-V was we've been doing ASIPs for years, application-specific processors. RISC-V solved a big problem we had, which is how do you actually work within standards? So it's a standard ISA, but it's also an extensible ISA. So use it with the Codasip tools. What customers can do is they can analyze their design. They can take a spec, either way. They can update the model that we use of a processor. We have these RISC-V models. And from that, we automatically generate the full SDK and the full HDK. Since some customers don't want to do that, we will do it for them. As just as part of our standard IP deliverable, if a customer says we want these instructions, we can go and do it. So it's very easy to take these designs, and we'll generate a fully automated, updated SDK and HDK. So you get all your instruction set simulators, you get your SDK, the LLVM GNU-based tool chains, everything that you would normally need, full verification environments, constrained random environments, everything you need to go and integrate on both hardware and software is automatically updated. So you add an instruction, everything knows about it, and you can instantly go to work with it. So that's a good thing. So now we've got implementation taken care of. We've got a RISC-V that you can, in hours or days, go off and customize. So what's next? So I think most of you probably saw this at the last workshop. One of our partners, which is SecureRF, did a talk on some of the extensions we'd put into their RISC-V core for accelerating their digital signing. And that we were able to, it basically took about 2 days to turn around their design. They gave us the instructions they needed. We were able to quickly modify, turn around, and have fully functional SDK and HDK for them. So that's taking care of the processing, but that's only part of it. I think there's a reason that Samsung's asked 2 questions about debug so far, because debug and bring up is a really big problem. We've got debug built into our cores, and we have the debug tools, but debug of the processor is just one part of the problem. So then we started working with UltraSoC, and UltraSoC have a presentation later today, and they can talk about their stuff way more intelligently than I can. But what it allows us to do is instrument the design with their IP that gives not only then the processor level debug, but you have SoC level debug. You can start doing protocol analysis on the buses. You can start to see what is going on within your design, and you can even start writing rules and special breakpoints to do security monitoring within the chip. So it's a very powerful, flexible environment. The reason we're interested, though, is it helps customers get their chips up and running as quickly as possible, because that's the next problem. After you've got a design, got the chip back, how do you make sure it's working quickly and easily? And so the types of problems that they solve is, is the security done correctly? Why does the system hang or go into deadlock? Why is the interconnect slow, or the CPU? Why is DMA misbehaving? All of these typically challenging problems, they have solutions for. And so they're going to talk more about some of their debug work later. But for us, we wanted to work with them so that when we get the chips back, customers can get them up and running in days instead of weeks. So that's the debug layer. So we've taken care of implementation gone from 68 weeks down to sub 10 weeks. You've got the processor that you can customize. You can add all your custom instructions if you wish, or you can work with the standard core, get extremely good power and performance. You've now got the debug in there, so you can start to bring up the chip really quickly and easily. So that leaves one problem, and people have been talking about it. What's the software layer? So for Codasip, as I said before, when we generate a core, we automatically generate a whole SDK and the hardware development kit as well. The SDK is based on LLVM. We generate an LLVM compiler. And this is using the standard LLVM. We take the knowledge from our model, we update the sources of the LLVM and generate a new LLVM on the fly. So we have LLVM working for RISC-V. It's on parity across a broad range of benchmarks with the GCC that the solution is out there. But what makes LLVM interesting in this case is it works very well with some of the existing programming solutions out there. So one of our other partners, CodePlay, have a rich layered programming model that goes everything from graph programming all the way down to device-specific programming. And it relies on LLVM. Now, because we have the LLVM backend being generated for the RISC-V core and for any extensions that you choose to put into that core, what we're now able to do is work with CodePlay, and we can layer everything on top. So now you can get, whether it be device-specific programming, higher level language enablers with OpenCL, going up to the very highest levels with TensorFlow. So what we can do is we can work now with their whole device stack. But more importantly, once you've written on those device stacks, you can start to profile the design and add new enhancements to the core. And everything just starts to work together seamlessly. You go, you run your program, your profile, you go, you know what, I need to add this, this function to the core. You can add it, regenerate. It all happens in a closed loop automatically, really quickly. And so you've got the device specific at the LLVM level. You can then go up to the higher level languages with OpenCL that's going to work across one core or multiple cores. You can go up to SciCL, and then all the way up to TensorFlow at the end. But the important thing is every one of these layers is based on an open standard. So while the solutions we're talking about aren't open source, it's all based on open standards. It's all easily able to be deployed and used by customers. And you don't have to use the whole stack that I'm talking about. You can go and pick any little piece of it for the design. It all works on a standard infrastructure. All of the partners are building their infrastructure around Eclipse. We've got plugins for each other's. Our debug plugins go straight into the UltraSoC debug interface. So it all just works seamlessly together. But more importantly, what it does is it allows you to get from a concept to a silicon in really short amount of time while still keeping control. For some people, they want to just hand off, as Jack was explaining with Sci-5 model, they want to hand off and leave off most of the complexity. But other design customers that we work with will coming to us and say, we want to keep in control, but we need to make this quick and simple and easy. So what this has done, it makes it much quicker. Everything is proven individually, and we've put research and development effort across all 4 companies to make it work together. And as I said, it's all based on open standards. And what we're doing is we are putting this, we're putting our money and where our mouth is. We've done the R&D integration at this point. Before the end of the year, we'll be doing test chips. We'll be taping out the test chips. We're going to make those test chips available to anyone who is interested. We're also exploring, additional partnerships that may make the parts generally available. There's a dev board very similar to what Jack was showing with Sci-5. We are looking to how we can add more collaborators in this ecosystem. So if you've got particular things people are interested in, I'd be more than happy to hear. We have the resources to commit to this. But the aim is to give you that platform, from a prototype, get 100 devices in a few weeks with working silicon, and make it so RISC-V isn't seen as risky. It's to take all the risk out of this. And what I can tell you is the level of interest from RISC-V is just phenomenal, not just because in the room here. As a commercial provider, I have never seen the level of interest for any product as RISC-V generates. And that's the end of my talk, and I think I've probably kept things on time even, which is shocking for me.
Any questions for Neil?
Yes, Frank.
So, good seeing you. So my head's, and I apologize if that's a stupid question, is maybe more on licensing. I'm still first learning this here, or starting to learn this. So my head's spinning as to the separation of the line between my IP, if I have an idea, which I now implemented with Codasip, and I have I used my UltraSoC friends debug to put, and to satisfy Samsung later on. The question is really around what of my IP, how do I protect my IP? That's a weird word, but to go back into the open source. And open source is kind of a two-way street, right? A lot of things are put back. How do I actually now keep my pieces kind of differentiate at the top of the iceberg thing? So how do you do this in the Codasip?
So in the case of, as I said, we're not open. The stuff we do is not, we leverage open standards. We're not an open source. So some of the tools that we generate are open source, and they may have a GCC license, although we try to always have an alternative to that in order to protect your IP. So if you put extensions into the RISC-V core, the LLVM that we generate, your LLVM allows us not to have to publish the source to your design. So likewise, we are developing our own, we do generate a QEMU model for different processors and other instruction set simulators. We're developing our own alternative to QEMU, because QEMU is a GCC license, which causes no end of pain for some of our customers. So by default, nothing you do is required to be released. And that's, because we are a commercial company, but that's where we spend our time and effort making sure that people can protect it. Now, you can choose to release things, but that's purely customers' prerogative. Everything by default is protected and locked down. It's your choice what you do with it. There's absolutely no obligation.
Hi, Dave Patterson from UC Berkeley and Google.
Yep.
Why do you think there's such a reaction to RISC-V that you talked about from customers?
I think it's a combination of multiple things. One is, right now a lot of customers are getting nervous about ARM because one of two reasons. One is ARM was using their position to extract more funds than not. And I think the Sci-5 guys had an interesting blog post a while ago talking about the experiences of one of the customers that came to them where ARM wouldn't give them access to the Fast Start program. For instance,
to the what?
To their Fast Start, or no, Quick Start, I think it's called. Design Start. Too many different versions out there. So part of it is just the accessibility. RISC-V is easily accessible. But the other thing is that I think fundamentally it changes the way people think about processor design and SoC design. So if you think about how people make a decision to build an SoC today, one of the first decisions they have to make is, what processor am I going to use? They make that decision at the very beginning, and it locks them in for pretty much for perpetuity in that design. If a customer says, I can use RISC-V, and they make that decision early on in the design, they can go and start building. And then later, as they get a more hashed out version of their design, they can then say, well, what RISC-V will I use? Which processor vendor is going to have the best processor for my job? Is it going to be open source? Is it going to be a commercial vendor? Is there a DSP? So it separates this whole buying decision from the design decision. And that is something that I think a lot of people have been very interested in. As a startup, it's changed the way people interact with us, because we always used to get the problem of, well, how do we know you as a startup you're going to be around in 5 years? With RISC-V, they go, well, that's not a problem. If you're not around, there'll be someone else around, or I can go grab the open source.
So it's the open instruction set means you can pick an instruction set without picking tying yourself to a company.
Correct.
And then it reduces the risk of using young companies. Yeah. Okay, thanks.
And I think the ARM being acquired also helped.
ARM being acquired by a large company.
Yeah.
Okay.
Rishi or Nikhil from BlueSpec.
Yep.
I have a question about the UltraSoC layer.
Yep.
2 questions. One is this instrumentation just during simulation or in the delivered chips, number 1? And number 2, in both those cases, what's the overhead in simulation? What performance costs and in the chip resource and other costs?
So the intent is if people want to use the UltraSoC, it is in the chip that you get delivered. We're working, so there was an announcement today, but there'd been a previous announcement I think last week with UltraSoC and ourselves. But UltraSoC ourselves, Basand, are putting it into silicon so we can actually do the measurements in terms of what the overhead is. It's extremely lightweight. I don't know if the UltraSoC guys want to say give a number. But I think they're going to talk about it later. But it will be in the hardware as well as in the simulation models, and the overhead is very light, and so yeah.
Hi, Steve Cox with Synopsys.
I think I've met you before, Steve.
I've seen you too. A couple of questions, a technical one and a business one.
Yep.
I noticed you didn't have Cormark per megahertz numbers on your slides. You have 2 implementations. Do you care to comment?
So I actually don't. The numbers are on the. If you want, I can give you a data sheet. We have. I don't know the numbers off the top of my head. Because we're doing the RISC-V instruction set and we've got the 3-stage and the 5-stage. It's effectively the same as the Rocket and the Z-Scale.
Well, you said they were modified, they were similar, but not the same.
But they're within the same order of magnitude. The way that they're different, our 3-stage one has some a subset of the privileged mode spec. So we have a subset to allow people to do some amount of privileged mode on the 3-stage, and on the 5-stage, it's roughly Rocket. But I have the numbers, and I give them anyone that's interested. I can give them. I'm not trying to keep them secret. I just didn't have them on the slide.
Okay. And this one may be a modified version of Don's question from earlier, which is the first part, which is what he asked, is how much does it cost? But there's an underlying one, which I'm curious about. You're really representing 4 different companies. So do I have to sign license agreements with each of those 4 different companies and everybody negotiates their own terms? And that sounds problematic.
Yeah. So it's a really good question that I can't answer at this point. We've started the collaboration. We're doing the technical work at first. For some of the partners, there are multi-way agreements within there. So, for instance, in the case of Basand, you don't have to deal with Codasip if you want our core. We're getting that business side sorted out. But as you know, that is usually a much harder problem to solve than the technical problems.
Thanks, Neil.
And just one comment on the core marks, and just to make sure everyone is aware, the performance of these cores. Our aim is we want to make it easy to modify, and as everyone has said before, you can get 10x performance improvements just by making minor changes that are still within the RISC-V spec.
Alex Solmaknikov. I used to work with Tensilica tools a lot in the past, and this was actually very nice tool set. I mean, it worked great.
Yep.
But the problem is it didn't work from business point of view, right? So could you say something about why this time is different?
Yeah.
Or is it?
Yeah. So yes, it's different. So so Codasip began as a vendor of software for doing processor design. We became an IP company because everyone kept on saying, we don't want to build our own processors. We want you to give us customized ones. And in that model, it starts to look a little bit like the Tensilica model. There's a couple of differences. One is every tool we generate from an open source version of the tool. So it's LLVM, it's GNU tools, and we don't put a license in them. So they're freely distributable by our customers to their end users. So unlike, say, Tensilica and Synopsys tools where they get tied down to a particular core implementation, as the customers can freely distribute them as they wish for their cores. So that's a big difference from the traditional ones. And the extensibility and the rate at which you can change these cores is much higher. Best if you have specific, I don't know if that answered the question or not. I saw a raised eyebrow, so if I missed the question, just please follow up.
No. Okay.
Okay.
Did you have someone over there, Dom? Nope. They withdrew their question. I'm just going to give you a mic, Don.
It's too interesting.
Don Stark from Google again. So just to look at the baseband part of it, there's been a couple of efforts in the past. There's like hard copy from Altera, and there's, Toshiba's had structured ASICs. In general, that approach hasn't been very successful commercially. So, and one of the issues seems to be, getting from sort of small volume to larger volume. So maybe talk about, one, what's different this time, and two, if at some point I want to go beyond my 100 chips to, say 100,000, right? So how do I do that without incurring all the expenses that you've saved me from initially?
So I think the people to answer that best are the baseband guys who are here. But the short version is baseband actually have a whole slew of offerings, and they will actually take people down that route, and they can fully harden the design to get to that scaling of hundreds of thousands of millions of units, and it's still within it's a process that they have. They can go down, fully harden it, fully customize it, get the extra power, get the extra performance, and get the lower cost down to pennies a device if you happen to need it. So they have that technology. It's not just while they have the metal configurable standard cell and the porting of the metal copy, they also have full implementation, and they will work with customers to do that through the whole life cycle of the product. So that's one thing that is different. I think the other thing that is different is the type of customers, at least from Codasip's perspective, we're targeting has been the IoT type designs, and the performance requirements for those are much lower. It's not as extreme as, say, trying to squeeze out, I used to be a telecommunications systems designer, when you're trying to do a networking or a telecoms chip, and we would work with those types of technologies, and you couldn't get the performance that you needed. In this case, you can get the performance within the power, within the cost, and it's just a coming together of everything that is in there. I think Jack was publishing the numbers with using TSMC 180. A lot of these designs are in these older nodes. Here we're talking about 65 and 40 nanometer, and what they can do is they can port a 28 nanometer Xilinx type design and have it run at a higher performance level in the 65. Yeah. The difference is it's an independent company. So you have that option of going not just the metal copy, but then fully optimized flow later on. And because they've got the IP in-house, it's a much more predictable business practice. But since I don't know the full intricacies of how they do that, I know they're here, so I could make the introduction and you can ask the question directly. That's the problem when I'm trying to talk on behalf of 4 companies. I'm dangerous enough talking about Codasip. Once I start talking about others, it gets really hairy. And there was no question on debug.
Yeah.
Come on, I was ready, please.
All right. Thanks, Neil.
Thank you.